Okay, what is up? All right, so let me grab my handy stylus here. Nice. And let's get back into it. All right. So I imagine everybody is very stoked up for spring break. I imagine very few people will probably watch the next lecture since it's a bonus lecture. All the same, I still encourage you to check it out if you want to. Maybe not live if you don't feel like it, but talk a little bit about the maximum modulus principle and some more about harmonic functions with a little bit of nice applications to some boundary value problems in engineering and physics. But today we're just going to finish out section 2.4. This is the last section that will appear on your exam, which goes live tomorrow. Don't worry, we've basically got everything. All that's really left at all is a nice little aside about the fundamental theorem of algebra and a nice inequality that is extremely easy to prove, along with two other results that are similarly easy and immediate consequences of Cauchy's integral formula, but are maybe not as automatically, they're very immediate consequences, but they're maybe not obvious consequences because they have profound implications. Louisville's theorem and Morera's theorem. So let us kind of take a little journey back through what we've talked about in 2.4 and then close it out. So we began by talking about the index of a closed path. Intuitively, what we want the index to be is we want the index to be a way of measuring how many times a curve wraps around a point. That is, we're looking at how many times one thing spins around another thing. You've got a point, you want to know how many times you've gone around it. Just once, or did you go around it twice? Did you do it again? 3 times? Did you go around it once clockwise and then once counterclockwise for kind of like a net of 0 or something? You know, this kind of thing. So the index of a closed path is what counts this. And the thing about it, though, is that we need to actually construct a device that does this. So we want to count the number of times a curve goes around a point, but it's not maybe necessarily immediately clear what that actually means. After all, we can come up with some kind of complicated and brutal looking curves that maybe intersect themselves and do all sorts of crazy stuff. And maybe you start to ask yourself, like, hey, what the heck? How do I even know? How do I even know how to do this? And so what we did is we came back to one of our good old friends, this integral that kind of keeps coming up, this thing where we go, hey, what gives? It's not 0, and everything else we keep going. Integral around a closed contour is 0. But then this is the kind of archetypal example of when classic results like Cauchy's theorem fail for certain things. That is, analyticity is important to actually get 0 out of some of these contour integrals, and the kind of classic thing that fails to be analytic somewhere is the integral around the unit circle of the function 1 over z. This guy is not analytic right at the middle of that circle. Okay. And we in fact know that it's equal to 2 pi I. So we're just integrating this function 1 over z around the unit circle counterclockwise, and we get out 2 pi I. Okay. If we divide by 2 pi I, we get 1. So maybe this isn't totally intuitive right away, but this should probably count. This is counted how many times we went around, right? We know that if we went around again, we would get out 2 because of the additivity of contours, right? That is, integrate f gamma 1, gamma 2, and you get out, gamma 1 plus gamma 2, right? Some business like that. So if we went again, we'd get another one out, right? Okay. So it's not necessarily unreasonable to think that the quantity that gets measured by 1 over 2 pi I, the integral around some curve of this, is maybe going to count what we want. So we know via deformation theorems that if you bend up a curve a little bit, bend it up without passing through zero, that is if they're homotopic in the region of the complex plane set minus the origin, then it maybe is the case that they wind around the same number of times or something like that. And so we went through and we got out this nice device called the index, which basically just let us take advantage of the fact that by doing exactly this kind of logic with, like, using additivity on paths that, have compatible beginning and end points, and the fact that we got out what we wanted just by dividing by 2 pi I, we built a device that counted what we wanted, the index. We had to do some stuff to prove that. We had to go through and we had to actually show that we were getting out an integer. We had to show that it was invariant under homotopies of closed curves in appropriate regions. We had to do all that, and then what we ended up getting to was this amazing thing called Cauchy's integral formula. Cauchy's integral formula, if you recall, said that if we had a function f that's analytic on a region A, and gamma is any closed curve in A that is homotopic to a point, then for any z in A that's not on gamma, we can evaluate this integral in terms of an index and a function evaluation. Or said a little bit differently, we can get the values of an analytic function by counting the number of times a curve wraps around a point and then integrating along that curve some function that kind of takes into account the center of that curve in a certain way, the center of like a circle, or what that point is. This is z minus z naught business, tells you what point you're evaluating it at. This is actually kind of crazy. We said it's really wild because what it really means is that the value of an analytic function is determined by its boundary values, as we might say, something like that. That is, the value of a function at a point is determined by its values on any curve enclosing that point that lies in its domain of analyticity, provided that that curve is homotopic to a point in that domain. So this is kind of a cool little trick. Basically, in a certain sense, it says that analytic functions play well with homotopies, and in terms of their analytic, their differential structure, with using integrals and all of that. What this integral formula let us do was quite a number of things. So this integral formula we went through and we proved it on out and did all sorts of stuff. It let us evaluate certain integrals very easily. For example, we could integrate e to the z over z about the unit circle, and notice z is the same as z minus 0. So, oh, hey, that's 2 pi I times the index of the curve, which is 1, and times the function e to the z evaluated at 0. So it was 2 pi I. Amazing. One of the easiest, most useful tricks for calculation. But also, it's totally reasonable to look at that integral that you see in, I think I might have made, there you go. This integral we see right over here, this integral about gamma of f of z, z minus c naught dz, and say, hey, what about just integrals like that in general? That is, if I build a function g of z as 1 over 2 pi I integral about gamma of g of zeta, zeta minus z dz, for some curve gamma in the complex plane and g a continuous function defined along the image of gamma. Okay, what about these guys? What about starting with the right hand side of that Cauchy integral formula and saying, hey, do I get out an analytic function? I know I can use analytic functions to get things that look like this, but can I use things like this to get analytic functions? And as it turns out, yes, you can get functions that are analytic on the complex plane sans the image of the curve we're using in this integral of Cauchy type. And in fact, these guys are infinitely differentiable with the cool fact that their kth derivative is just multiply the thing by k factorial, and in the denominator, throw on a k plus 1th power. Kind of nice. Sort of the thing to think about here is that, and this is a very weak analogy. This is not, I'm not saying this in any sort of a technical way, but I do think it is helpful if you're just trying to remember it. Think about sort of something like when you're doing calculus and you have like the power rule, right? You're decreasing by 1, right? You know, you're going from like x to the third down to x squared, right? You know, you take the derivative of x to the third, you get 3x squared, right? So you're decreasing a power by 1. Since this is in the denominator, when you add 1, you're really decreasing by 1, right? This is zeta minus z to the negative quantity k plus 1, right? So you can still think of that as sort of like we're decreasing a power by 1, right? In a certain sense. We're adding 1 to something in the denominator of a fraction. So this is sort of like a power rule in a certain way, which is kind of neat. That's a useful feature of analytic functions, or of integrals of Cauchy type. And as I kind of, well, we already learned, and I'm sort of spoiling it right now, and this is what I'm saying, it's the differentiating under the integral sign business, is that similarly, you know, starting with an integral of Cauchy type, hey, do we get an analytic function? Yes. Well, do analytic functions enjoy the same nice property in terms of how they can be derived? Yes. Okay. And this was the Cauchy integral formula for derivatives. So analytic functions basically have, like I was saying, kind of this analog of like the power rule from regular old calculus in terms of how to derive them. You just have to use the integral representation. All right, kind of cool. So we were rushing through this right at the end of class. I wanted to say a little tiny bit more about it just in case anyone felt a little bit weird about the proof. Basically, in a nutshell, we spent some more time on it last time, but in the very simplest way, all you have to do is you define a function g of z as f of z times the index about gamma with respect to z, right? And then you just use the fact, use the fact that I can represent f of z in terms of this integral form. Hey, that's an integral of Cauchy type, so it's infinitely differentiable. And then I get that the derivatives of g are like this. But hey, g is also defined in terms of, so we have the derivatives of g are like this, but hey, look, g is defined in terms of f in this index. Now, as it turns out, the index, as we know, is constant for points z on the interior of a curve, right? So if I have, you know, some crazy loop-de-doo curve is going all over, and I have z some point in here, if I like went over to some other point here, the index would be the same. As long as I'm staying inside the curve, the index remains the same. Okay, so it's constant. That is, when I do a derivative, this bad boy, this piece right here, is just constant, and that's the whole business of it. So since the kth derivative will just be, then, you know, you got a constant here, and this is, you know, you just get the kth derivative of f, right? Pull that index right out. Bada boom, easy enough. Okay, now we're into the new stuff. Okay, so where are we at? What is going on? What we've got is we've got a way to represent analytic functions in terms of integrals, and we've got nice formulas for their kth derivatives in terms of integrals, and all of this came out of Cauchy's theorem. all that's really left right here is a nice inequality, and it's not too bad. So this inequality, known as Cauchy's inequality, or Cauchy's inequalities, I suppose we should say, because there's more than one, realistically. There's one for every derivative. Let me get a good-sized highlighter here for us. That's nice. That's good. Yeah, that's a good opacity. Okay. So theorem 2.4.7, Cauchy's inequalities. So we've got f, an analytic function on a region A, gamma, a circle of radius capital R, and center z naught that lies in A. Okay. And we're going to assume that the disk composed of values z that are within R from the center of that circle lies in A. That is, we have gamma, a circle of radius R centered at z naught, and we want not only the circle's boundary to lie in A, but also the inside of it. Okay. Then, suppose that f in modulus is less than m for all z on gamma. What we get out in this case is that for k equals 0, 1, 2, so on and so on, the kth derivative of f at z naught is less than or equal to k factorial over r to the k times m. What this means in short form says that, the derivatives of an analytic function, since being analytic means you have an analytic derivative, which of course means that you have infinitely many analytic derivatives, right? Infinitely differentiable, with each derivative continuing to be differentiable itself in a nice way. Where the nice way is, not just differentiable, but analytic, where, satisfying the Cauchy-Riemann equations and all that. What is happening when we differentiate is that we can get out things that get big, but not too fast. That's sort of the answer that Cauchy's inequalities tell us. That is, holomorphic functions are, so the fact that you have f bounded by m right here, if you put in the 0, then you'll just get 1 r to the 0, so it's 1 times m. It's just, you recover this statement. But if you put in like, 1, 2, so on and so on, right? This is saying that the derivatives can't get big too quickly, right? You might expect that this will actually come up in something like a, I don't know, like a Taylor series. We'll end up using this. It just means that the derivatives of analytic functions can't get big too quickly. As it turns out, they don't get big too quickly, so we can make power series. And we'll do that soon in the next section, but next chapter. But let's prove this guy. So, since the index about gamma of gamma with respect to z naught is 1, since gamma is a circle with center z naught, Cauchy's integral formula tells us, this last piece we were just talking about the proof of, tells us that the kth derivative is equal to k factorial over 2 pi I times the contour integral about gamma of f of zeta minus z naught to the k plus 1th power d zeta. Okay, so the kth derivative at z naught, got it in this nice form. All right, so just throw a modulus bar on either side. Okay, we can pull out the constant. We can pull out that k factorial and 2 pi. All right. Now, I already know that f of zeta over zeta minus z to the k plus 1, well, I'm integrating around gamma, right? How far away are things here? Well, they're exactly a distance of r, right? So we could break this modulus up on top and on bottom. So we've got r to the k plus 1 on the bottom, just because the distance from a point on a circle to its center is r, because we're looking at a circle of radius r. Okay, we get that k plus 1 right there. And then we're assuming that f is less than m in modulus. So obviously the integrand is less than or equal to m over r to the k plus 1. Okay, so just looking at this left-hand side and then using this nice bound that we've got before. Remember, we multiply by the length of gamma, and then we have a bound on this thing. Okay, so we're going to get just that k factorial over 2 pi just carries on through, and then m r k plus 1, length of gamma, but length of gamma is 2 pi times r, right? Since it's the circumference of that circle. Oh, 2 pi, okay, that cancels out, so that is just gonna, so this guy right here is 2 pi r. That's what gamma is, or length of gamma is. Cancel out that 2 pi, cancel out that 2 pi right there, r, and then get rid of that plus 1, right? So no more plus 1 right there. So that's just r to the k. Oh, hey, k factorial m over r to the k, right? And wouldn't you know it, that's what we wanted. We're done. Easy. So that's not a terrible proof in the slightest, but it gives us something that's kind of crazy. And this is a sweet theorem that you will get a ton of use out of. It is a fantastic result because it is just so dang nice and easy to say. It is called Liouville's theorem. Fun bit of history. I don't know if you know this. I think maybe they mentioned it in your textbook. I don't know why you know it. Liouville's theorem shouldn't be called that. It should be called Gorsat's theorem. It was called Liouville's theorem, or really it should be called Gauss's theorem probably, or one of Gauss's theorems. Someone had just seen it in some notes that Liouville had passed along or used in a class. It was not first proved by Liouville, so history remembers this as a theorem of Liouville's, but it was not a theorem of his. Liouville getting credit where he doesn't deserve it, though. I'm sure Liouville's a great guy, dead for hundreds of years. I don't care. But just a bit of history. Anyways, theorem 2.4.8, the inaptly named Liouville's theorem. If f is entire, meaning analytic everywhere, and there is a constant, and this is bad scan, m, such that in modulus f is less than or equal to m for all z in the complex plane, then f is constant. There are no bounded entire functions that aren't constant. It is every bounded entire function is constant. If you have an entire function that's not constant, it's unbounded. It grows as big as you want it to. That's nuts. This is so different from the real case. For example, think about, I don't know, cosine. That is a function that is differentiable, infinitely differentiable, and infinitely continuously differentiable. And it's bounded, as are all of its derivatives. You can't have bounded, non-constant analytic functions. That's nuts. That's crazy. Okay. Well, let's see. Why is this? It's an immediate consequence of the Cauchy inequalities. So Cauchy inequalities for k equals 1 shows that for any z naught in C, we have that f prime of z naught is less than m over r. Holding z naught fixed and letting r go to infinity, a kind of crazy trick, since we only are just taking gamma to be a circle with radius r centered at z naught, right? Then we have, this has got to be true, right? For any circle. So if it's true for a circle of radius 1, it'll be true for a circle of radius 2, and so on, and so on, and so on. Normally this m would grow to accommodate it or something like that. But notice, if we're already assuming that we've got boundedness, then as we take this away, that m just stays the same, right? So as r gets really big, m doesn't get any bigger, and so it goes to 0. What? That's crazy. So its first derivative is 0. Oh. That means that, or its first derivative is 0 in modulus at that point, and therefore it's 0 at that point. Kind of obvious reasoning, right? Since that's true for every point in C, that's a constant function. A function with a zero derivative everywhere. A constant function. Mind blown. Amazing. Liouville's theorem. Okay, what can we do with Liouville's theorem? Well, we can prove a result that you have known for a long time, but have probably never seen a proof of, the fundamental theorem of algebra. Something that says, hey, how many, what are the zeros of a polynomial that has a polynomial of degree n, has n zeros, some potentially in the complex plane, of course, counting multiplicity. How do you prove this? We always use this as a fact. How do you prove it? Here's a proof using Liouville's theorem. We'll go through this. Really, it's a fun application of it. There's a slightly shorter way to technically do this, but it would rely on us accepting certain limits that are not well justified quite yet. So we'll just say it in its full glory. So we're going to let A0, A1, all the way up through AN. These are a collection of n plus 1 complex numbers, and we're going to suppose that for n greater than or equal to 1, or that n is greater than or equal to 1, and an is not equal to 0. So we'll define a function p of z, a polynomial in z, as a0 plus a1 z plus a2 z squared, all the way up to an z to the n. Our claim is that there exists a point z0 in C, z0 in C, such that this polynomial is 0. That is, since an is not equal to 0 and n is greater than or equal to 1, what we're saying is that the only polynomials that have no zeros are non-zero polynomials of degree 0, right? So if we show this, then we can, repeatedly apply it and get the classic fundamental theorem of algebra, where we say, hey, a polynomial of degree n has n roots counting multiplicities. Okay, so we're going to start by supposing that this is not the case. That is, we're going to prove by contradiction. So we're going to suppose that it's not the case. We're going to suppose that p of z naught is not equal to 0 for every z naught in C. Then, since it's never 0, the function f of z, defined as 1 over p, is entire, right? Oh, 1 over polynomial, it's never 0? Yeah, it's entire. Okay. Now, p of z, and hence f of z, of course, neither of them are constant, because an is not equal to 0, and n is greater than or equal to 1, right? So that means that there's at least a0 plus a1z, right? That's the smallest case we're considering, and in that case, a1 would be non-zero, so it's not constant. Okay, so it suffices by Liouville's theorem to show that it's not bounded. That is, if we're trying to show that something has to break here, or to show that it is bounded, if we're trying to show that something breaks here, we'll show that our assumptions lead to something that we know isn't true. That is, we'll show that these assumptions would say that this function is then entire and bounded and not constant. But Liouville's theorem says that the only bounded entire functions are constant, so this must not be the case, meaning that there must be some point z0 such that p of z0 is equal to 0. It's a proof by contradiction, classic. Okay, the first thing we'll do is we'll show that p of z goes to infinity as z does as well, or equivalently, since f is 1 over p, that f of z goes to 0 as z goes to infinity. Okay, easy enough. All this really means is that given an m greater than 0, there has to be a number k greater than 0, such that for z greater than k in modulus, p of z is greater than m. Okay, easy enough. That means we have to show that if you put in big enough inputs in modulus, then you get big outputs in modulus. All right, fair enough. So p of z, we already know how it's defined, a0 plus a1, z, so on, up to an, z to the n. Notice that we can do a nice little manipulation right here and go, hey, p of z in modulus is greater than or equal to the modulus of an, z to the n, and then minus a0 minus a1, z minus an minus 1, z to the n minus 1. So everything except everything individually modularized, right, We're subtracting off here everything except that last term. That last term sits right there. Why? How are we doing this? Well, we just go, hey, look, let's do a little reorganization, right? A sub the ANZN, ANZ to the N is equal to the P to the Z minus all of those other terms, right? Just, throw a minus right here, minus, and then dot, dot, dot. Let me just do dot, 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 A, N minus 1, Z to the N minus 1, right? Equals. See what I'm saying? Throw a minus right here, and then you subtract it all over. And then you get this nice statement right here. So you just apply the triangle inequality, right? So, okay, fair enough. So you just do the triangle inequality on this guy, and then you pull those other terms over. It's kind of a weird step. If I actually write it down, it would take a long time to write down. But just basically do modulus on either side, right? Then split everything up with a less than or equal to, right? Like less than or equal to, and then we split everything up. We put pluses as we split it up, right? Dot, 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 plus. See what I'm saying? Okay, and then we'll subtract it all over, and we get that this piece over here is less than or equal to P of Z in modulus. Does that sound fair? Okay, it's just some algebra. This comes from the triangle inequality and that little fact that we can just subtract everything except this nth term. Okay, cool. Now we'll let A be equal to, and this is just going to be a real number. It's the sum of the moduli of the coefficients all the way up to n minus 1, from 0 up to n minus 1. So the sum of the moduli of everything except of all the coefficients except for that last one, which remember we've assumed is not equal to 0. Okay. If z is greater than 1 in modulus, then notice we can do this nice trick. So pull out z to the n minus 1 from all of these terms right up in here, right? Got p of z, all that stuff. Pull out z to the n minus 1. We'll get the a sub n, z to the 1 now because I pulled out n minus 1 from that n, right? And then all the rest of them I'm getting these modulus z to the n minus 1 and so on all the way up to 1 with this this last guy right here. You can see what's on the screen. Okay. Now, what am I going to do? Well, notice these are just the pieces of A, but they're divided by something that's greater than 1, right? So I could just get rid of those guys since that's making them smaller and I'm subtracting them. I could, subtract something bigger and definitely get something that's even less than what I've got here, right? Okay, so I'll do that. I'll just get rid of them. Then I'll have this guy, all the way up there. But hey, that's just A. So I've got z to the n minus 1 in modulus, and then modulus nth coefficient, modulus z minus A. Okay, kind of a little bit of brutal manipulation right there. Now we'll take k to be the max of 1 and m plus a divided by the modulus of the nth coefficient. Okay, so all we're doing here is just making sure that if this thing better at least be 1. If it's not, we'll take 1. If z is bigger than k, notice, all we'll have to do is just, basically you can plug everything in here nicely, right? So z is greater than k, plug in this piece, m plus a divided by modulus of the nth coefficient. Okay, plug that in right here. Cancel these guys out, right? Oh, hey, I've got m plus a, I've got a minus a plus a, so that's just an m. Now, if we're plugging this piece in, it means that z is at least bigger in modulus than 1. So that's certainly something to the n minus 1th power that's greater than 1, right? Is going to be bigger than 1. So it's something bigger than 1 times m. So that's definitely bigger than m. So we can at least say that p of z in modulus is greater than or equal to m when z is greater than k for k chosen in this fashion. Okay. So just flip everything around. Is put p on the bottom, modulus p on the bottom, put m on the bottom, and flip the inequality. So 1 over modulus p of z is less than or equal to 1 over m. But hey, on the set of z less than k, z and modulus less than k, this function is bounded in absolute value because it is continuous. So if this bound for 1 over p of z is denoted by L, then on all of C, we have that 1 over p of z is less than or equal to the max of 1 over m or an L, right? So that is on this this compact subset, a continuous function on a compact subset is bounded, right? You get out a biggest value. Okay. In norm or in modulus here, we have that this guy, this non-constant, by our assumption, entire function, we've just shown that it's bounded. Or we've shown that f is bounded, sorry. F is bounded on C, and since we're doing this by contradiction, we're going, oh, hey, wait a second, we've got a non-constant entire function that's bounded. That can't happen. That's what Liouville's theorem says we can never do. Entire functions are bounded only when they're constant. So hey, we just proved the fundamental theorem of algebra. Oh, sweet, cool. Now we're ready to take college algebra. Nice. Good to go. So it's kind of a cool application. We'll round out the section with this kind of like, that was just sort of an aside, a nice little application. You can't do a complex analysis class without proving the fundamental theorem of algebra. We'll round out the section though with another big result on par with Liouville's theorem and its usefulness. Morera's theorem. Morera's theorem gives us something like a partial converse to Cauchy's theorem. So Cauchy's theorem says that if you've got an analytic function and an appropriate curve, a closed curve, then when you do a contour integral, it's 0. You can ask the kind of reverse question: when you've got contour integrals 0, do you have an analytic function? So if we start with f a let me get my highlighter here. Morera's theorem says that if f is continuous on a region A and the integral around every closed curve in A is 0, then f is analytic on A, and f is equal to f prime, big F prime, for some analytic function f on A. So not only is it analytic, but it's got an analytic antiderivative. That's kind of obvious. The existence of the antiderivative, at least, that just comes from vanishing of integrals around closed curves in the path independence theorem. That was something that we started with in this section, 2.1.9. I kind of made that less readable. Path independence theorem, existence of the antiderivative is implied by vanishing of integrals around closed curves. Okay, fine. So that's fair enough. The antiderivative f will obviously be analytic. After all, its derivative is f, right? Okay. So, by the Cauchy integral formula for derivatives, it's infinitely differentiable. Oh, okay. That's kind of smooth, right? In particular, f double prime is equal to f prime. And that exists. Kind of nice, right? So since you have, you get this analytic function, because, it's got an antiderivative, right? So it's definitely differentiable, obviously. The antiderivative is definitely differentiable, but hey, this is an analytic function. Cauchy integral formula gives us infinitely differentiable. So certainly if it's infinitely differentiable, then its derivatives are also infinitely differentiable. Bada boom, that is a smooth little dumb kind of proof. It feels so simple that you go like, is that right? That must be wrong. But no, it works. So kind of cool. And this leads us to nice results like corollary 2.4.11, which is another very useful one. So if you have a function that's continuous on a region A and analytic on A, except maybe at some point z0 in A, then f is analytic on A. That is, continuous functions that are analytic on regions can't fail to be analytic at isolated points like that. Notice this is not contradicted by things like 1 over z, because 1 over z is not continuous at the point z naught that we'd be looking at the point 0 in that case. That is, 1 over z is not continuous on the entire region A right there, right? Okay, it's only continuous on A sans z naught. So you need continuity on the whole thing and analyticity on everything except a point. Okay. So to fail, if you fail both, then that's fine, but you can't just fail analyticity while having continuity. Okay, kind of cool. So to show that you get analyticity at z naught, we restrict our attention to a small disk contained in A about that point, some disk of radius epsilon centered at z naught. So pick any closed curve gamma in this disk, then when you integrate around it, it's 0, right? Okay, by Cauchy's theorem for a disk, the strengthened form that we did back in 2.3, 2.3.5. Okay, so any closed curve in this disk, you integrate around it, you get 0. Wait a second, Morera's theorem then implies that F is analytic on the disk. Oh, notice Morera's theorem, we just needed continuity on the region A. We already have continuity on a region A. Bada boom. Easy. So that's pretty smooth. That is a pretty nice little trick. And that's everything we've got. That's section 2.4 in a nutshell. There's a little tiny bit more in there about logarithms, but it's not worth talking about right now. I think I said last time that I might try to do a proof of the differentiability of Cauchy type integrals. I left this proof off because it's kind of long. The reason that it gets so long, I think we'll talk about this briefly just before we go too far, just because it is worth mentioning. The proof of theorem 2.4.5 as they give in your textbook is actually a very good proof. It's fine. It's a good way to do it. It's the way to do it. Now, it relies on a few different things. In particular, the parts that I think that make it very cumbersome, it's just some epsilons and deltas and stuff. Nothing too brutal or anything. Classic bounding things to show that you get what you want, analyticity and stuff like that. Basically the same exact way we went about a lot of the other proofs where we bounded things above, showed we could make that bound small, showed that means something 0. Okay, cool. That kind of stuff. But we use a lot of identities in this proof that are not obvious, and they're not cool. They're just tricks. Well, there is some intuition for it. We'll talk about maybe later if we get a chance. We probably won't end up talking about it, but you'll get maybe if you might be able to get some perspective on why these tricks are useful or something if you really wanted to. I don't off the top of my head have a great answer, but you might be able to get some sense of this when we talk about fractional linear transformations later on. Right now, though, they're just algebra tricks, basically. Rewriting something like z minus z naught over zeta minus z naught squared times zeta minus z as this long series of different fractions and stuff. You have to use something like that. Or later on, writing 1 over zeta minus z to the n as 1 over zeta minus z to the n minus 1 times zeta minus z naught plus z minus zeta, or z minus z naught over zeta minus z to the n zeta minus z naught. Oh my god, what ridiculous algebraic substitutions. Okay, you just do some induction, you do some stuff like this, and it's not super enlightening, I would say, in terms of the proofs we get in this class. It is not something that makes us feel like, oh man, I really learned something. It's something that you kind of have to slog through. So we're not going to go through that. But if you want to, you can go through it. It is a good thing to do if you feel like you really want to understand it. Most of the algebraic techniques that they use, little tricks, just come down to finding a common denominator, and then it all comes together. But how you would come up with them just off the top of your head is not, they're kind of unenlightening for that reason, because you just go like, I guess that works, but how did you think of it? Glad someone did, but I don't think that we're spending too much of our time on in the class at this point. Instead, you guys may be interested in talking a little bit about the exam that comes tomorrow. So the exam tomorrow will release. Oh, sorry, my son is having a little bit of breakdown. Poor little guy has just started. We think he just started teething. He's chewing on everything and having a bad time of it. So hopefully he doesn't full on breakdown right now. Oh, good. Yeah. Okay. Anyways, the exam will release on WoW Courses along with an announcement tonight at 12:01 a.m. Just right away at midnight, and you will have until 11:59 p.m. on Monday after break to get it in, and it hopefully that's enough time. It's not super long. I've tried to have a nice mix of things. It does definitely tend a little bit more heavily towards some of the more recent stuff, since everything builds together, and it's easier to test more concepts with stuff later on than giving a whole lot more problems, more explicitly covering things early on. But I've tried to also split out at least a fair number of problems that only require things from earlier on. So if you feel it all shakier, you can still demonstrate your knowledge on things that maybe you feel better about. So, so I think that it shouldn't be too bad. If you have any questions, please shoot me an email. I'll be checking my email all break long, and I will be available to answer questions and all of that. Homework keys are up. Grades for homework should be up. And yeah, cool. So I think we'll call that for tonight. I will see you on Friday if you want that bonus lecture. If not, no worries. Have a wonderful spring break. Be safe, and hopefully the exam goes well and doesn't detract from it. Yeah. See you later.